Hello everyone, thanks for attending this talk. My name is Matteo Brucato and I will present to you our work on stochastic package queries and how they can be very helpful in solving important optimization problems decision makers encounter in a variety of domains. In real life, in a multitude of cases, hard decisions have to be made in the face of uncertainty. That is, when the data values are noisy or unknown and must be estimated using predictive models. For example, in finance, investors have to decide which stocks to buy today in order to maximize their revenue tomorrow. Problems like these are also common in healthcare, the travel industry, manufacturing and supply chain, just to name a few. There are a multitude of individual solutions for each of these problems in each of these industries. All of these solutions, however, exist outside of a database, despite the fact that the data is often stored in a database system to begin with. As a result, the database is merely used as a data container, and the data just flows out of the database into the custom-made programs and the solutions then back into the database. This process is cumbersome, error-prone, and not easily transferable to new decision problems as they arise. By doing these analytics in the database itself, we promote efficient, seamless, and agile analytics workflows applicable to a variety of problems, also offering the typical data management functionalities for free. In this talk, I will use the investment portfolio as a running example. Suppose you want to invest in a set of stocks. Your objective is to find the best set of stocks that, when sold back, will give you the highest possible return. This corresponds to selecting a set of rows from the stock investments table, with multiplicities corresponding to the number of shares per stock. We call such a set of rows a package. If we knew the gain each stock can yield after the holding period, we could write this as a package query in PACL, the package query language, where we simply set a budget constraint and an objective to maximize the sum of the gains. Unfortunately, the future gain is not known. It is a random variable. We indicate random variables in the table with question marks. Since gain is a random variable in the query, the sum of gains is also a random variable. We can therefore try to maximize its expectation. We call our extended query language Stochastic PACL, or SPACL for short. Investors understand that trying to maximize the expected gain incurs risk, that is, a solution might lead to a large loss. Therefore, investors want to control the risk, typically using chance or probabilistic constraints. In this example, we want the probability of losing $10 or more to be small. We can express this constraint as losing less than $10 with probability at least 95%. In the financial world and in many other domains, the random variables are too complex to be treated analytically. What people typically do is to run simulations of them in a Monte Carlo fashion. So we employ the Monte Carlo DB data model, which uses specific user-defined functions called VG functions to generate scenarios or possible worlds for each of the random variables in the input table. The original stochastic query is then replaced with a deterministic version of it that only works with the scenarios, replacing the original probability distribution with an empirical version. The probabilistic constraint ensures that a portfolio makes more than negative $10 in at least 95% of the scenarios, and the objective is to pick the solution with the highest average gain over the scenarios. This problem is a deterministic integer linear program, or DILP for short. To solve such a query, we first generate some scenarios, solve the DILP, and then test the solution against a huge set of out-of-sample scenarios to check if it's actually feasible. Such checking is relatively fast, which is why the set can be huge. In this case, for instance, the solution that picks tuples 1 and 2 only satisfies 30% of the out-of-sample scenarios, rather than 95%, and therefore it is infeasible. This happens because of what people call the optimizer's curse. If you use too few scenarios when you solve the DILP, the solver tends to view the world too optimistically and gives you solutions that are in reality infeasible. Then the question is there a way to theoretically determine a priori how many scenarios will overcome the curse? Unfortunately, existing theory only provides very conservative bounds. Specifically, the theory says that you need at least O of n scenarios, where n is the number of rows, to make sure that your solutions will not suffer from the curse. This is not a useful guideline because in a database setting, n is typically large. Even with just thousands of tuples, the size of your problems will grow to millions, and solvers can't possibly handle such huge problems. The state-of-the-art in solving stochastic ILPs is an algorithm that tries more and more scenarios incrementally until the solution becomes feasible. again with respect to the huge set of out-of-sample scenarios. From now on, I'm going to refer to this huge set as the validation set, and we will assume that a validation feasible solution is indeed truly feasible from the user's perspective. This algorithm starts with some small number of scenarios m, solves the corresponding DILP and checks feasibility on the validation set. If the solution is infeasible, for instance it only satisfies 70% of the validation scenarios, the algorithm increases m and tries again. The advantage of this approach is that we have a chance to keep the number of scenarios used in the optimization phase low. We only increment m up to the point when solutions become feasible. But as you have probably guessed, since we call this algorithm naive, this approach has major drawbacks. The size of the DILP grows rapidly as the number of scenarios increases. So what can happen is that we can easily reach the point where the solver can't handle the growing number of scenarios, but the solution hasn't become feasible yet, and so we have spent a lot of time to only find infeasible solutions. As naive progresses, he has a higher success rate in finding feasible solutions. Here I'm plotting the time it takes to reach a higher and higher fraction of feasible solutions when we run naive multiple times by simply changing their initial random seed for each run. As you can see in this example, naive never reaches 100% success rate. It gets stuck around 60%, meaning that if you run naive 10 times, only 6 of those runs will yield a feasible solution. The time to reach this unsatisfactory result is also very high, about 4 hours, for a table with only 4,000 tuples. Is this an unlucky case? Not really. In our 3 workloads with 23 queries, naive reaches 100% feasibility in only 7 queries. In many cases, it doesn't go beyond 50% feasibility, and in some cases, it even gets stuck at 0%, meaning no matter what the initial random seed is, you'll always get an infeasible result. So we definitely need to do better than that, and this failure is exactly what motivates our solution summary search, which I'm going to describe next. The key idea is to replace the purely random scenarios we've talked about so far with more conservative versions of them. A set of purely random scenarios we've seen can induce the solver to think that the constraints are easy to satisfy. The solver will solve a large DILP only to find that the solution is cursed to be infeasible in reality. So the solver will have to try again and again and again. By replacing random scenarios with more conservative, worst-case versions of them, where the world seems more unlucky than it is, we can trick the solver into searching harder for a feasible DILP solution that will be truly feasible in the end. So we will typically require many fewer iterations than naive to find a truly feasible solution. At the same time, we are also reducing the number of scenarios considerably, so there will be many fewer constraints, and even though these constraints are harder to satisfy, overall each iteration will be much faster. However, with this approach there is also a caveat. You don't want your summaries to be too conservative, otherwise the solution will be highly suboptimal. We will go back to this concept soon. A simple way to construct a conservative summary is to take the minimum of a set of scenarios tuple-wise. Any solution that satisfies the summary must also satisfy each of the summarized scenarios, and may satisfy even more scenarios beyond that. And we can easily control the amount of conservativeness by taking min of fewer or more scenarios. This suggests a methodology to find the best summary given our m scenarios, which is a key step of our overall solution algorithm, which we call summary search. Suppose we have 10 scenarios to work with. We start by taking the min of 3 scenarios to construct an initial summary. We then solve the DILP using only the summary, and then we check if the solution is actually feasible. Suppose that it's not. We need to increase feasibility. Summary search does so by increasing the conservativeness of the summary. And that's easily done by taking the min of more scenarios, 8 in our example. Suppose the solution is now feasible. It is likely suboptimal. Now we also have the chance to improve on optimality. Summary search does so by now reducing the conservativeness, taking the min of fewer scenarios, 5 in our example. In the paper, we show how to conservatively test if a solution is 1 plus epsilon away from optimal. In our example, we find that we are done. The paper gives the details of exactly how we systematically search for the best number of scenarios to summarize, and how we select a particular set of scenarios to form the summary. Here we show again the time to reach feasibility. As you can see, summary search starts immediately with high feasibility rate. It reaches 100% feasibility and very fast, orders of magnitude faster than what naive takes to just reach 60% feasibility. In the paper we show similar trends for all the other 22 feasible queries. So far I have assumed that only one summary is constructed. However, using only one summary may not be sufficient to achieve a desired approximation. We can construct more summaries in an intuitive way by taking mins of separate groups of scenarios. Summary search systematically searches for the best number Z of summaries and best number M of scenarios. We skip the details because of time constraints. But here we show that increasing the number of summaries, shown on the x-axis as the percentage of the number of scenarios, allows summary search to improve the optimality of our solutions while maintaining their feasibility. On the y-axis, 1 indicates the best solution. When we use too many summaries, each based on a small number of scenarios, the summaries become too similar to the actual scenarios and summary search starts behaving like naive, producing infeasible solutions, shown by markers without colors. In conclusion, we motivated in-database support for constrained optimization under uncertainty, and provided a SQL extension that allows formal specification of an important class of such problems as stochastic package queries. We provided a scalable solution to find feasible and approximately optimal solutions to stochastic package queries that succeeds when existing approaches fail and allows agile and efficient decision-making in the face of uncertainty. As part of future work, we plan to extend the classes of queries we can support to sequential optimization problems, where the decision maker needs to make a sequence of decisions rather than a one-off decision. Thanks a lot for your attention, and I'm happy to answer your questions.